Hey, Mr. Dimitrievich, today we're going to learn about the types of chemical reactions.
Yeah, so instead of memorizing millions and millions of reactions, we're actually learning about five essentially templates of how reactions fit, and hopefully then we'll be able to predict how reactions work.
So it turns out there, like you said, there's 5 types. So what's the first type we want to talk about?
Well, let's talk about synthesis first.
So synthesis, that comes from the word synthesize. So what does that actually mean?
Essentially, what we do is we're taking two individual things and we're putting them together to form something else. So if you look at my puppets here, you have an A and an X, and you put them together and become AX.
So we would write chemically A plus X makes AX. So you still have the elements A, whatever that is, and X, and then they turn into AX. That makes sense. So Mr. Dimitrievich, what would be an example of a synthesis reaction?
Well, typically what we're going to have a word equation. So let's do magnesium plus oxygen, and let's put an arrow.
So Mg is magnesium plus oxygen. Now, tricky folks, O, it's not O, it's plus O2, and that makes magnesium oxide. Now, it's a little tricky on what the product is. It's not MgO2, is it, Mr. Dimitrievich? How do I figure that out?
And so anytime you're putting two things together, two elements together, when they become part of a compound, you have to balance their charges just like we do at any other type of reaction.
So as we call, Mg is plus 2, and O is minus 2, so they already cancel out, so it makes MgO. So when I do that, when I need to balance that, obviously that's not balanced, so I draw my arrows underneath, and so I've got an O problem. My Mg's are fine, so I put a 2 here. That gives me 2 oxygens, but then what I need to do, of course, is add a 2 in front of magnesium, and that's the reaction. And Mr. Dimitrievich, let's actually watch this reaction take place.
Let's see it.
So this is an example of magnesium burning in oxygen. This is a synthesis example. And in order to get it kick-started, we're going to put it into a flame. Now, if you take a look at all this powder right here, this is actually magnesium oxide.
So, Mr. Demetrius, that was super cool watching that fiery thing. So that's the first type of reaction, the synthesis reaction. Now let's take a look. What's the second type?
The second type is a decomposition. And the nice thing about decomposition is it literally is the exact opposite of a synthesis.
So what would that formula be, sort of in the symbolic form?
So it literally be exactly opposite. So let's go AX, and that's going to break apart into A plus X.
Perfect, perfect. Now, what would be a good example of a decomposition reaction?
So a good example of that would be water. And water, we all know, is H2O. And in this case, it's a liquid. And when it breaks apart into its elements. So in this case, two elements would be what, Mr. Bergman?
I want to say H plus O, right?
Yeah, except we learned something just a little bit ago, and it's super important. Elements by themselves that are part of Brinkelhoff, what do we have to do?
Diatomic. H2 and O2. But again, we have a problem. When we try to balance this equation, it doesn't look like it's right, but we can only make it right by changing the coefficients. So I have a problem with oxygen. On this side, I only have 1 O. On this side, I have 2 O's. To fix that, I have to put a 2 here. But that creates a problem with my H's, and now I have 4 H's, but that is simply easily fixed by putting a 2 there. So I'll tell you what, let's take a look at an example of a decomposition reaction.
So this is an example of decomposition of water, and in order to cause water to break apart, we're going to zap it with electricity. So if you take a look, there's bubbles coming off here, and that is the hydrogen and oxygen that are getting separated from the water.
Well, that was also cool, Mr. Dimitri. Sorry, so we've done synthesis reactions, we've done decomposition reaction. What's number 3?
Let's try single replacement.
So plus replacement. So you're replacing something. So what's like the general form with our A's and X's and such?
So let's do this. Let's go A plus B plus BX.
Oh, so something's replacing. I gotta believe like the A and the B are gonna trade places. Replacing because B is connected to X. So what it turns out to...
Yeah, it just swaps. So A is going to take the place of B, and B gets kicked to the curb.
Oops. kick to the curb. So it's a single replacement. Now, as a note, folks, what I also want you to jot down, that this is always going to be the BX or the AX is going to be some kind of an ionic compound, right? So metal bonded to non-metal. And this could be either, A could either be a metal, usually a metal. Sometimes it could be a non-metal, where actually the A takes the place of the non-metal. But usually, as you recall, the non-metal ionic compound comes second. So yeah, an example, Mr. Demetrius, what would be a good example of this?
Well, let's try doing aluminum, plus copper nitrate.
Now, copper has a charge, actually copper 2 nitrate would be CuNO3 2. Now, there is also copper 1 nitrate, but we're going to just do copper 2 nitrate. And by the way, I've done the charge game with copper positive 2 and nitrate with a negative 1 charge. And then arrow, well, then something has to replace. And
so if you take a look, the A replaces the B. So isn't our A aluminum in this case?
Yeah, this is the A. Copper. This is the B, so the aluminum's going to make the copper. Now, folks, again, remember we like to do little scratch pads. Aluminum, when it has a charge, is a charge of +3. Nitrate, polyatomic ion table, is -1. So it's going to make Al, +3, -1. Hopefully you're getting good at this. NO3, 3, because of the charge game. And then it kicks to the curb, Mr. Copper.
Here.
Oh, sad, sad. Okay, so by the way, this is a solid, and this is only going to work if this is aqueous. We're going to learn a little bit more about it in the next video. And then this is a aqueous, and this is a solid. But it's not balanced, so because and again, the rule that you like to say, Mr. Demetrius, start with the most complex one. And the most complex one seems to me the aluminum right here. So let's put lines in front of everybody. So we've got 1 aluminum and 1 aluminum, so I'm happy. But I've got 3 nitrates, and here I've got 2 nitrates. So I need to get them to 6, like lowest common multiple, right? And so if I put a 2 here, that gives me 6 nitrates, but that makes me have to put a 3 in front of the copper, okay? And then that creates 3 coppers on this side. So over on this side, I need 3 coppers. To do my aluminums, I have 2 aluminums here, and I can fix it by putting a 2 here. All right, so that's a single replacement reaction. Let's take a look at an example. Mr. Demetrius, that was awesome. That was super cool to see how that copper formed. Oh man, that was awesome. All right, well, next type.
Let's do a double replacement.
All right, replacement, double. I think I'm getting the idea. So what's the general form?
So that would be like AX plus BY.
Oh, and they're like trade partners, right?
Yeah, I don't know if you remember, there was a show that was popular for a while. It was called Wife Swap, which is a terrible show, but essentially,
no, I never saw it.
Yeah, I didn't either. Really, I didn't. Essentially, what happens is the partner swap. So the best way to do is to keep maybe your X and the Y in the same spot, and then just have your A and your B switch places. All
right, yeah, so it's a double replacement. They switch partners. Okay, let's do an example of what that might look like. So what would be a good example of this?
Yeah, so let's try lead 2 nitrate plus sodium chloride. And both of these are aqueous, as you're going to see in the next little video.
So as a note, this is important. I'm doing these in my head. Pb is a +2, nitrate has a -1 charge. That cancels out. Sodium +1, chloride -1. And it's going to form, in fact, let's just write that down. Pb is +2, nitrate is -1. Notice how I did this. Na is +1, and Cl is -1. All right, so this is a little scratch pad because I'm going to rebuild everything on the other side, and they're going to trade partners. Now, you can't have the negatives get with the negatives because they won't add up to 0. So when I put the lead with the chloride, it's going to be PbCl2, Pb and Cl2, all right? Because +1, -2, and then sodium with nitrate will be NaNO3, +1, -1. That's an unbalanced equation. Arrow, arrow, or underline, underline to do my coefficients. My nitrates are 2. I'm going to fix it by putting 2 here. So that gives me 2 sodiums. I pop over here, give myself 2 sodiums. 2 sodiums, then I've got 2 chlorides. Yo-ho! Look at that. 2 chlorides makes 2 chlorides. 1 lead makes 1 lead. That's the answer. All right, so that's a double replacement reaction. Hey, let's take a look at that, like an example.
That would be combustion.
Now, combustion reactions are the coolest ones because they're like fiery things, right? Combustion means burning, and they actually mean a reaction with oxygen. And the general form of this reaction is, I'm going to say CHO plus O2 always makes CO2 and H2O. Now, when I say CHO, what I'm really referring to is a compound that contains carbons, hydrogens, and then also sometimes oxygens. So, Mr. Dimitris, what would be a good example of a combustion reaction?
Well, let's take a look at something that's in all of our gas valves, methane.
So methane, you don't necessarily need to know the formula of that. We won't teach that to you. But methane is just simply CH4, and it's got C's and H's. And if I say the combustion of this, the rest of it is always the same, plus oxygen. When you burn it, it always makes carbon dioxide and water. That is the reaction right there. All right, or let me show you another example that might be a little weird. What if I have CH3OH? That's called methanol, not that important that you know that. But if I say methanol, and I give you the formula, and it combusts, what's the rest of this reaction? Can I tell you what the rest of this reaction is?
Yeah, that's the beauty of this. Combustion always is the same thing. It reacts with oxygen, and it forms carbon dioxide and water.
Now, the trick on these ones is how to balance them. And again, we talked about this in a previous video. Remember when you're balancing these, it's the CHO2 rule. You do the carbons first, then the oxygens, or then the hydrogens, and then the oxygens, and then you double it. So let's just quickly do just the first one here, and then we'll look at an example. Arrows in front. So the carbons first. There's one carbon on this side, one carbon on this side. Check. We're good. Hydrogen, I got 4. I got 2. All right, I need to put a 2 here. That gives me 4. And lastly, I do the oxygens. I've got 2 oxygens on the right. I've got 2 times 1 or 2 oxygens on the left. So I need a total of 2 plus 2 equals 4. And I need to put a 2 here. I didn't have to double this one because it worked out. And this other one you may have to double. I think you get the idea. Let's take a look at an example. That was super awesome, Mr. Dimitris. I love fire. I'm a bit of a pyromaniac, and I bet some of you are too in class. Hey, that's it. The 5 types of reactions. We just want to make sure you can recognize them. Any last words, Mr. Dimitris?
No, if you remember these 5 templates, the AX plus B, etc., those, you're going to do pretty well this unit.
I'll see you in class.
See you next time.